This webinar is about MNEST project, an EIT manufacturing project. MNEST is the network for empowering people in added value manufacturing systems and technology, and has as main goal to create a network of teaching and learning factories around Europe. Today, we are going to have this webinar about smart manufacturing driven by digital technologies. And I will now present our speakers. First, we will have Gil Gonçalves from the Faculty of Engineering of the University of Porto.
Hello, good morning. Thank you, Anna.
Hi, good morning, Gil. Good morning. So Gil is professor at the faculty and also a coordinator of one of the areas of 16DEC. 16DEC, the Research Center for Systems and Technology of the University of Porto. Gil has been leading several research projects, as well as also being present as technology officer or executive officer in several startups in Portugal. So Gil is going to share his presentation with Rui Pinto. Good morning, Rui.
Hi, Anna. Can you hear me?
Yes, we can hear you very well. Thank you. So Rui also works at 16DEC. He has been working there for a couple of years now. And also he teaches at the Faculty of Engineering of the University of Porto. And after Rui, we will have João Basto. Good morning, João. So João is engineering manager at INESC TEC, a research center in the north of Portugal. And he started his career as business analyst at one of the INESC TEC spin-offs, LTP Labs. And afterwards, he came back to INESC as a senior researcher in the area of artificial intelligence and optimization. Today, he also teaches at the Faculty of Engineering of the University of Porto. So I guess we can start with this learning event, and I will pass to Gil, who is going to present the digital transformation in manufacturing companies, opportunities, and challenges. Thank you, Gil, for being with us today.
Thank you very much, Anna. Thank you very much for the introduction, and welcome everyone. So as Anna just mentioned, I'm going to briefly introduce you what are the global trends and the main challenges in manufacturing companies these days, and also try to identify how the digital transformation can help to address these trends. I need some help here with the slides. I'm not sure if this is working or not. Currently, I'm not. Oh. Okay, so now it's working. So in terms of the global trends, we could look at this from the perspective of the technology, and we could discuss about the different industrial revolutions. But I think it's best that we look at this not from the technology side, but from the market side. And what we can see is that nowadays we are at a stage where we have gone through different areas where we started with craft production, so a small number of products, but very different between themselves. Then we went to mass production with huge volumes of similar products. Then we entered into an area of mass customization, And nowadays we are in a market where personalized production is key. So global markets where the customers are personalizing their products. They are selecting specific features which vary from customer to customer. So from the company point of view, this means that there is a huge demand for customer-specific production, where you have to be able to build or to produce in large volumes, but with individual design, which means that you have very small lots and one-piece flow in your production plant. At the same time, there are trends related with sustainability. So you need to be highly efficient, you need to reduce your emissions, you have to be able to reuse not only the materials, but also the equipments and the machinery, and you have to reduce waste. And then there is this global trend on digitization and networking. So you need to be able to connect every machinery in your shop floor, guarantee reconfiguration, flexibility, and evolution. There are integrated value chains between the company and suppliers and customers, and there is a constant change in this network. Looking at these challenges, we see that nowadays the supply chains are more and more complex, and the connection between the different nodes in the supply chain is getting stronger. So you are exchanging a lot of data and information in a very fast and efficient way with your customers and with your suppliers. There is also this changing customer. So customers are always at the center, and you have to be able to adapt to their needs and to provide what they are asking in terms of specific features. There is also something that came up in the last couple of years, which is related to this uncertainty in terms of macroeconomy and also in the geopolitical context, with several crises across the world in different geographical areas. And this means that for the supply chains and for the global supply chains, this is an additional risk, which means that you need to be more efficient and be able to reconfigure your supply chain quite fast. From the perspective of the company, this challenges and this global trends means that companies need to better understand what are the possibilities and what are the benefits and the new opportunities that the new technologies bring. So you have to understand what is the impact of introducing digital twins, what is the impact of using robotics, artificial intelligence, and other technologies in your company. And there is another dimension which is related with the human skills. So with this big change in terms of the technologies, there is also a difficulty in finding the right resources, finding the right collaborators for the company. So from the perspective of the company, this digital transformation means that you need to understand the technologies and you need to identify the best human resources for it. In terms of the digital transformation trends, and this is something which is not new, you probably heard of this many times. Industry 4.0 is here, which is a global trend, the fourth revolution. And the main idea is that you will be integrating new technologies in the shop floor, connecting all the machinery, connecting machinery to people, and then connecting to your external partners. This means using the Internet of Things for interconnecting physical objects, using digital twins to create digital replicas of your equipments and your processes, use advanced data analytics to better understand how the processes are going and to optimize process parameters, and to introduce robotics and automation to improve efficiency and to improve the production capability. And this is where MNESTRIS and where where this project that Anna introduced in the beginning comes in. So here at Porto, we have what we call the Porto Factory Unit. So this is something that gathers facilities from INEGI, from FEUP and INESC TEC, and we are trying to work together to build this teaching and learning factory, which can be then available to local and also to international companies which are giving the first steps in this new reality. Together with INESC TEC, FEUP is working on the perspective of the ICT-driven smart manufacturing. And our idea is to provide a set of resources, learning and teaching activities, which will allow companies to better understand the challenges and the opportunities that lie with this digital transformation and virtualization of production systems. And today in this webinar, our idea is to present this teaching and learning factory, so the Porto Factory Unit from the ICT-driven perspective, and to give you some examples of the technologies that you can explore and understand within this factory unit. And so we will have here two things that will be presented. Rui will address Dinosaur, which is a distributed platform at the fog level for the implementation and reconfiguration of cyber-physical production systems. And then João will address a different topic related with discrete event simulation. So thank you very much, and looking forward for your comments and questions. And Rui, now it's up to you.
Very nice introduction. So in fact, I will present the Dinosaur Technology. And as you said, this technology was developed under the digital transformation trends that you mentioned before. So basically, Dinosaur, it's a technology which involves an industrial standard, which is the IC 61499. So probably you already heard about this standard, and this standard targets the distributed function blocks functionalities. So basically, you want to embed some software, some code within our own industrial machines, and for this we can use function blocks, which are units of software in order to develop some distributed control within our industrial systems. So within this function block concept, we can encapsulate software modules, we can exchange data between encapsulated modules within the edge or fog layer. We can also reconfigure software and also the physical devices that are in our production lines. And also with this, we can develop applications for industrial distributed systems, such as cyber-physical production systems. So in this case, we have developed Dinosaur based on these implementations. So next slide, please. Thank you. And trying to understand a little bit better what is a function block. So like I said before, a function block is a functional software unit. So basically, we execute a certain software under a function block, and we can trigger that execution based on input events. And we can also have input and output variables, which can be used to exchange data between function blocks. So the idea is to develop several function blocks that can connect all the function blocks among themselves in order to create a pipeline, a configuration pipeline or a function block pipeline, which can be used to deploy later the respective software within our cyber physical production system. Next slide, please. Okay, and regarding the EAC 61499, there are two topics that it's worth mentioning. So one of them is the development environment, and another one is the runtime environment. So regarding the development environment, we use 4DAC IDE to be able to develop and deploy function block pipelines. So the 4DAC IDE, it's based on the Eclipse project. So if you already know Eclipse IDE to develop some Java code or C code, it's pretty much the same user interface, okay? But in this case, the 4DAC implements this standard, and it can be used to develop and deploy function blocks. The next topic that I mentioned before is the runtime environment. So since we are integrating 4DAC with this standard, so basically in practice, this means that we should implement a runtime environment which will enable us to execute function blocks, okay? And the runtime environment that we have on Dinosaur, it's called Fort. So next slide, please. Thank you very much. So Fort implements the 61499 standard. So this is a small portable implementation of the standard, and supports online reconfiguration of the applications and also real-time execution of all function blocks according to this standard, okay? So the main advantages here are a distributed architecture, so we can deploy function blocks within a distributed system, so we don't need to deploy software into all the machines one by one. We can do it in one single time in a distributed way. Another advantage is the industrial standard, so this follows a well-known industrial standard that is already being used in PLCs and in distributed industrial systems, and it's edge-oriented. So the Dinosaur, it's a technology that can be used exactly to reconfigure software within these edge devices, not on the cloud device or on another layer. It's on the edge, which can bring many advantages because we don't have to access the PLC and edit or update the code that is executing there. We can remotely just deploy some new configurations instead of messing around with all the code that is already executing and working on the PLC. Regarding these advantages, there are two main disadvantages, which is the limited language support. So Fort right now is supported only on C++, and also the third-party integration, which it's non-existing. So Dinosaur was developed to tackle these challenges in order to bring some more languages support and also third-party integration according to the scenario of machine-to-machine communication. So in this case, next slide, please. So the overall system architecture of the Dinosaur, it's this, as you can see in this picture. So based on Forte, we developed Dinosaur, which implements function blocks that can be supported in Python, and also the third-party integration with external devices can be done via OPCW. So not only we can bring Python to the table, which it's a well-known language in data science and machine learning, but we also can integrate multiple devices in my industrial system based on the OPCW protocol. Next slide, please. So like I said before, OPCW is one of the main industrial machine-to-machine communication protocols, and since Dinosaur acts on the edge layer and implements OPCW, then the Dinosaur enables any external data to be automatically provided in an OPCW server for further system integration. So in our understanding, a Dinosaur is implemented in a physical device, and a Dinosaur on practice implements OPCW servers. So all Dinosaurs are OPCW servers, which have their own data to be provided to the outside, so other third-party devices can connect to this OPCW server and collect this information. Next slide, please. And finally, regarding Python, so recent trends show that Python is one of the main programming languages used for developing machine learning applications and within data science. So right now, Python supports several frameworks for machine learning, data science, and so on. And the idea behind using this language in Dinosaur, it's to enable the latest advantages in machine learning to be integrated at the edge level with existing shop floor equipment without the need of fog-based processing or the cloud-based processing, which sometimes can be a non-desirable feature within some industrial companies. Next slide, please. Well, and the development process, it's very simple. So first step, we need to develop our function blocks, which are based on two source files. One file, which is the Python, so contains the Python code, and another file, which is an XML file, which contains all the configurations to be connected with the EAC standard and the 4DAC development interface.
2 minutes.
Yeah, no, thank you. So the second step is to orchestrate these function blocks into a pipeline using the 4DAC. Sorry. The third step is to associate these function blocks into an actual physical device, and we can map these different function blocks to different physical devices. And then we can actually deploy the function blocks to the respective physical device, reconfiguring our industrial system and all of the physical devices that are connected to the network. Next slide, please. Well, and then I have three main use cases that we already experimented. So there are laboratory scenarios, but they can be used also in a real industrial scenario if we extend a little bit our implementation. So if you can move on to the next slide, please. So the first use case is the collision detection. So we have a mini robot manipulator with several sensors in their servo motors. And the idea is to predict a collision of the robotic manipulator with an operator, with a user. So in this case, we are using a random forest classifier. So this classifier sends an event to the controller function block to stop the robot manipulator every time there's a new collision that was detected. Next slide, please. So the next one is it's a collaboration between a universal robot and a gripper that was 3D printed. So we accumulated this 3D printed gripper into the universal robot manipulator. And then according to a certain task both of these devices should collaborate with each other, and then we can use several function blocks to control each device and communicate between one another. And finally, the last slide, please. Thank you. So this is an overall manufacturing application where we can have a sequential production process, and we need to simulate this kind of process so we can have multiple workstations with multiple function blocks simulating its behavior, replicating operation times, error times, and so on. So it's very easy to replicate or add new workstations to simulate other type of scenarios. So like I said before, it's a matter of extending our function block pipeline to enable this to a new scenario and possibly real industrial scenarios. And I think that's it for my presentation and Professor Gilles. So thank you very much, and I'm looking forward to reply to all your questions at the end. Thank you.
Thank you. So I have to say to our participants that you actually can put your questions to our speakers in the chat. So my colleague Ana Simões, I'm sure she is talking to you in the chat because we don't have visibility for that. And we are very happy to welcome your questions. And I think we have one right now. So Margarida Machado is asking, can Dinosaur be used and implemented in an industrial context, or is only available for education research purpose? I mean, is this software platform licensed and available for commercial purchase? So I turn back to Gilles and Rui for answering this question.
Mm-hmm. Yeah, maybe I can answer this. So basically, Dinosaur is already being used in some research projects within actual industrial enterprises. And we don't have a commercial licensee per se, but you can find Dinosaur available. So we have a GitHub repository public, so you can go there and clone the code and use Dinosaur as you please. So right now it's an open technology which you can use, and we already are being using this in real industrial scenarios, and for now everything it's working very well.
Thank you, Rui. So I have another question, which is from Ana Simões. What are the main barriers that companies are facing for the implementation of these advanced manufacturing technologies?
Maybe I can take this one. So
thank you.
I think there are two sorts of barriers. So first of all, it's the technology barrier. It's not easy to understand what are the technologies that are easier to implement and that provide better benefits for the problems that you have. So sometimes it would be helpful if companies could have an opportunity to test and experiment these technologies before investing in the solution, which is not easy. So I think that's one of the main barriers nowadays, is really to understand which technologies are providing more benefits at the stage where the company is. The other one is related with the human side. So these new technologies, they require a new skill set. And in some cases, it's not easy to find the right resources to use in the implementation and then in the deployment of these solutions. And that is why we think that something like this Porto factory unit, where companies can understand the technologies, can even provide some of their challenges to be dealt inside the factory unit, is a major advantage. So this could be an environment where companies understand what are the challenges, what are the opportunities of the new technologies, and also what are the requirements for their resources, and eventually already train some of the resources that they have.
Thank you, Gil and Rui, for your presentation and answering to the questions. And we will now move on to João Basto, who is now going to talk about simulation and digital twin, production system simulation and dashboard creation. Thank you, João, for being with us today.
Thank you, Anna. So my presentation, as you were saying, is about simulation and digital twin, which is nowadays a very trending topic. There's a bit of confusion between these two concepts, and I'll try to clarify what each one of them is. So I will do a brief presentation on production system simulation. Then we will cover dashboards, which are a tool very important to give very quickly inputs to the decision makers. And finally, we will talk about the digital twin topic on the area of shop floor data integration. So in terms of production system simulation, what is simulation? Well, simulation is a technique where we use a computer to create a replica of the operation of a real process or of a productive system. And the main usage of simulation came from the necessity, the need to analyze systems that have uncertainty in their behavior. If we have a system that we know always what will be the output in a certain time period, it's easy to analyze the system. But when we have stochastic, non-deterministic events that depend on probability distributions, such as stockouts in a supply chain or the demand of clients in a supply chain, or in more industrial terms, the time between failures of machines or the processing times of machines, we need to have a tool that allows us to analyze how this uncertainty will impact us. And what simulation does is it generates events. Basically, it generates what will happen in the future. For an example of the production system rolling, and it can do it several times because it can run long periods of time in a matter of seconds. And then it will allow us to have outputs of the key performance indicators of the systems. So where these abilities, where did they first start being used? Well, the first use of simulation was mainly for the design and operation of queuing systems. So when we think about restaurants, hospitals, supermarkets, things where we have queuings, we know that it's important to measure how many people we need to be serving the people who are our clients. We need to measure what is the estimated waiting time for a client, because we know that a lot of waiting time can lead the client feeling unsatisfied. And so this was the first application, and it began decades ago. And from there on, there have been several evolutions, and nowadays we work on a supply chain, on the management of inventory systems. And we also work, and this is the area that I will present, and the area where I mostly work on the design and operation of manufacturing systems. So, one idea that appears very related to simulation is modeling. Modeling is the process on which we build a simulation model. It's a process that assumes abstraction. So we will not take every detail of the real model and put into the simulation. We have to reduce the complexity. If we put all the details, the model will be so complex that it will take a long time for the computer to run. First of all, and we are putting things that are not important for the measures that we want to obtain. And when we complete this process of modeling, we have a simulation that we can run to, in fact, generate analysis and give inputs to our decision makers. But how do we model? Are we able to create a model of the process? Well, it depends on the school of or type of simulation that we are building. Mostly for manufacturing systems, we use a type of simulation called discrete event simulation. And the basis of discrete event simulation is you need to think of your system as a process. There's a flow, there are units that enter your system, and mostly when we talk about these units, we are talking about the pieces that you will fabric in your factory, and they enter as raw materials, and they suffer through a flow of several transformations until they become the product that you are going to sell. So these operations can be delays, they can be service from other resources, it can be the choice of branches of the process. One type of product goes one way, the other type of product goes the other way. And we will also have queues. As long as there's a competition for shared resources, the parts will have to wait to perform their operations, and we will have queues. So I think this process of modeling can be made more clear through a practical example. The example that I bring you is a factory where we have a production line, and the pieces are received in the production line, they are cut, and then they are painted. And so we can do this is a very simple example, and we can do a very simple flow of the process. There's the arrival, then the pieces go to a queue where they wait for the cutting stage, then they go to another queue, they are painted, and then they exit the line. And now we have a flow of the process, so we can create our model. And this is the example that we were discussing, implemented on FlexSim. So FlexSim is a simulation software where we can build this kind of models. And as you can see, what we are doing is a complete representation of the problem I was describing in this software. So we are creating a source, which is the element that creates the raw materials that are arriving to our factory. And then we have these visual components that we can use to represent the logic. So we are putting a queue to first store the materials, then we put a machine, a processor, where we will do the cutting, and then there's another queue, and now we are putting the painting machine. As you can see right now in the video, we have this ability of choosing the probability distributions that govern the processing time of each part in each machine, which is the main advantage of simulation. So we are able to define these probability distributions, and the simulation will use them to run. And now you can see that we had a small conveyor in the end. We are able to add these elements that, although they don't change the logic, they make the process graphically seem a lot more like what it is in real life. And now what we are doing here is we are setting the objects that enter the factory to change their shape when they are cut and to change their color when they are painted. Finally, we add some operators because we know that somebody has to do the transport from the queues to the machines. And as you can see, we are putting one operator to each machine, and the model is built. We start running, you can see the pieces flowing through the machines, and the operators are used to pick up the machines. So now we have, in a very simple form, we have created this model. But the thing is, we have a model, it looks like the factory, it has the logic of the factory, but we know that production managers and decision makers in the industry need very clear inputs to make their decisions, and this is just a model, what we saw. And so the way that we have to give inputs to our decision makers is to make dashboards. So dashboard is basically a tool that allows visualizing data and the reports of the most important key performance indicators of a system or of a business. And the good thing about dashboards is that they have interactive behaviors. So the user can not only check what is coming, the information that is coming, but he can also filter the information and select specifically what he wants to see. And in this kind of simulation models, it can be used to analyze the future performance of the productive system. So now you can see this is the same example, and now we are collecting the dashboards. We are measuring how many pieces we have in each of the queues, what is the evolution in terms of orders that we are sending and orders that we are concluding, and we are also measuring the main occupancy rate, so the utilization rate of each resource, to find out how much time they spent being used and how much time they are idle. And here in a more complex project that we make, you can see also that there is a high degree of customization to these dashboards. So we can make, in this case, for example, this was a factory that had a production plan that they were very interested to see if they were able to keep up with the production plan. So we can register in a table for the different production orders when they were launched to the factory, when they were concluded, and what is the expected due date. And we can very quickly trace the ratio of orders that we are completing without delays. So this was a very basic explanation of dashboards, but I hope you got this idea that they can be used to enhance the decision-making process. And finally, let's talk a bit about shop floor data integration and the concept of digital twin. So the digital twin, basically, the main difference to simulation is that in digital twins, we are integrating with shop floor data. We are building this digital replica of a real system too, but we have data coming from the shop floor to our system. This means that in each time instant, if we look to the real system and if we look to the digital twin, we have the same information. If a machine is working, then in the digital twin it will appear working, and if it's failing, it will appear failing. So there are two fundamental concepts that we need to create a digital twin. One is obvious, and it's so widely known, it's widely used, it's sensorization. We need sensors to capture this information, but then after capturing this information, we need to send it. And to send this information, we use something called Internet of Things. So Internet of Things is a concept that was born with the fourth industrial revolution. It's one of the key concepts of Industry 4.0, and it basically assures that we can connect the shop floor equipment, sensors, actuators, to the high-level services such as simulation, optimization, anything that composes a decision support system. And with shop floor data, we can not only feed this model, this digital twin automatically, we can enhance the decision-making process. And I have an example to show this. So picture a factory where we have several logistic resources that are used for transport, and suddenly one of the resources fail. Now we have two options. We can either use the yellow resource next to it to do its operation, or use the gray one. And what we can do with a digital twin, if we have everything connected in this platform that you are seeing, we have the simulation, the real-time database, the information system. So all the high-level architecture is connected to the low level, to the shop floor. What we can do is simply, when something fails, like that resource, we can send automatically an email to our production manager. So first of all, we can very quickly identify a failure. Second of all, we can trigger, as we send this email, we can automatically start running simulations to find out which is the best resource to compensate the failing resource. We run the simulations, we generate those dashboards that you saw, and we can send another email to the manager so that he can choose, okay, if I use resource A, I will have this productivity in my factory and this utilization rate. If I use option B, I will have these other KPIs. So we can very quickly, in an automatic form, send the best decisions to the managers to make an action to these unexpected events. So this is it. I hope I could bring a little of information and demystify these concepts. But if you have any further questions, please ask, and you have my contacts here if you want to clarify anything else. Thank you.
Thank you, João, for the presentation. It was indeed very clear, the presentation of the concepts, and I hope the participants can still have time to make some questions. We have here one from Ana Simões, and I mean, João, you have been working on these projects in several companies for the past years. And we know that each project is one project and all projects are different. But can you tell a little bit to our participants about your experience on the type of decisions that are connected to these projects in companies, and also usually how long do these projects take? Thank you.
Okay, thank you, Anna, for the question. So the simulation projects can in fact change a lot depending on the application. In industry, we have projects from the beginning of a factory to the normal operation of it. So for example, we had projects where a company wanted to design a new factory, and the objective was to understand what was the best layout to the company, given the production objectives that they had, the number of products, the expected production time. So we would help them build this new factory. But we also have projects where we are assessing the necessities for next year. For example, we have a company that has a factory, and they know that the demand will increase next year by 20%, and they want to make sure if the current warehouses they have are enough to store the products or not, and if they need any new machines to enhance their productivity. These are the main types of projects we did. We also did some things with evaluating the number of logistic resources necessary. In terms of time, there's also a range that can change, but I would say that between 1 to 3, 4 months, it's the time to have a simulation project, depending on the goals.
Thank you. Great. Thank you for being so clear on the various possibilities and ranges that we can count. And I hope this answers also the curiosity of our participants, also to get in contact with you in case they want to go in this adventure of creating simulation and digital twins to their factories. Thank you, João, for being here. So I guess no more questions in the chat. So yeah, just confirming. And so I guess this is our the closing of the session. So I wanted to point out that actually what you saw today are some examples, some samples of learning nuggets that have been produced during this year in MNEST project. And also, if we consider all the other projects that we have in the Porto factory unit, and we can count for about 20 different learning nuggets that have been created in this area of smart manufacturing driven by digital technologies. So, and what is going to happen with these nuggets? So actually, EIT Manufacturing has started last year, so this 2019, and 2020 is the first year where we have projects. So all these projects have created this diversity of learning nuggets that are going to be exploited in the so-called guided learning platform that is going to be being created and is going to be live next year. So next year, all these contents will be in this platform that can be used by companies to create their training programs for their employees, but also for creating programs for students in master's and PhD programs. So stay tuned. keep in touch, and we also will have MNEST proceeding to next year. So all these contents will be there, and we'll be happy to help you creating all these training programs for your companies or students or just interested people wanting to know more about smart manufacturing. We can have last words from our speakers. So some call for action to our participants. Gilles. So we cannot hear you, Gilles. Okay, thank you. Now we hear you.
Okay. So I was just saying that I cannot do anything else than to highlight what you just said. So next year we will have several programs ongoing, and if you want to know more, just come back to us, and I'm sure that there will be interesting learning opportunities, interesting technologies that can be explored, and hopefully we can help you to identify what are the technologies that better suit your needs, and also to help you get the required skills. So thank you very much, and have a nice day.
Thank you. So Rui, do you want to add something?
Yeah, I want to thank the opportunity for being here and present the technologies that we are developing within this project. It was a pleasure to work with all of you. And like you said, we will have a continuation for next year. So we want to extend our developments and try to reach as much partners as possible to make this available for everyone. Thank you.
Thank you. And João?
Well, I also would like to thank the opportunity to share a bit of my area of work in this webinar. I think this area is full of potential opportunities for companies. There's a big path to be taken in bringing these technologies and bringing this knowledge to the industry, and I think that we can achieve in the future great outputs mostly for the ability of companies to enhance their flexibility in production. And thank you.
Thank you all for this. So as last words, we still have one question right now. Claudio Santos from INEGI. And it's for you, João. He wants to ask you, the practical example of the digital twin is very good. However, it seems that the decision to change the production system is always left to the production manager. Self-adaptive systems have the potential to autonomously make such decision. In that sense, what level of smartness can we expect in advanced production systems in the next 5 years?
Well, I think the idea of self-adaptive systems, for me, it's great. It's one of the things that I even will be exploring in my PhD. So I really like that idea. I think it's still a bit early, if we are realistic, for having the open-mindedness of production managers to allow this kind of systems. I think for now we have a very difficult and gradual path to follow when it comes to enabling these systems in industry. I don't know if in 5 years I think in 5 years we will see some applications of it in the industry, but I don't expect a broad general introduction of these technologies in the industry. Maybe 15 years.
Okay, thank you for keeping us updated on the timelines. And okay, thank you so much for being today. And for closing, I must thank our communications manager of MNESTRIS, Ana Cristina Simões. So she was the leading of organization of this webinar. I also have to thank all the partners that have participated together with us in this project. and the communication service from INESC TEC that has done all the layouts and the communication instruments, and of course, Creative Cluster, who produced this webinar. Thank you all and see you soon. Bye-bye.